I'm going to kind of let these guys take you on a little tour of what we do, but I'll give you a little just basic kind of heads up of what this is. So I work in the electromagnetics and microwave group. Dr. Chamberlain works in the telecommunications and signal processing group. I think they may have renamed it something else now, but that's fine. We do lots of stuff together. I do a lot of antenna propagation and systems work, and he does a lot of algorithm and programming and other stuff. And so a lot of the stuff that we do just meshes very well together. You can see all these different projects around this room that are sitting around. We're going to talk about some of them. If you see something else that's hanging on a poster, on a whatever, you're welcome to ask a question. Each one of these guys is very well knowledgeable in all of this stuff. That's our air compressor. It conveniently comes on. But we do a full sort of full shop in here. We do everything from building PCBs and soldering things up, using components that are already put together. Sometimes we build our own components, we program our own radios, our own microcontrollers, everything else that we do. We can go from custom to off the shelf, but we put it all together. And we test things like different antennas, different ways of combining signals together, sensing. You'll see all these quadcopters that are sitting over here. They'll kind of explain what the project is that we're doing there. It's about RF landscaping. And we've got lots of other different things. You see this little double helix over here. That's a little project that we do. We kind of break things up into, you kind of think about this as there's basically a skill project, so you have to develop some skills, and then we've got a research project. We're really going after something new. Right? So you got to get some skills under your belt, and then you can go on and do some really great stuff with research. My research in particular deals a lot with, we've got some new stuff we're doing with swarms of different antennas on UAVs that fly around and coordinate with each other. We do a lot of work with fluidics and microfluidics, particle dispersion, so we actually pump particles through antennas much like your veins and arteries do, and that changes how the antennas work and perform. We've got a lot of stuff. We take smartphones, we tether these. In fact, there's a video playing behind you that you can sort of see someone tracking a smartphone, and we'll talk a little bit about what's going on there. We build these systems up, so if I take my phone out, my phone knows where I'm looking at, and so it puts a vector out in space, and so then I can have another setup. It's kind of like a dish antenna would be tracking, but it's flat. We can mount on a wall, and you can't see it. If I just point it around, it puts a beam on you, and I can say, hey, make this person stop transmitting, or I want to record what they're doing. Or maybe I'm just curious about who's interfering with my signal, and I just say, what are you doing over here? Stop it. I can tell who's doing what on what wireless. Service, everything else. So we do lots of these types of projects. We also got little UAVs that we build, not just quadcopters, all kinds of different stuff. So the first thing that we're going to do actually is split up into two groups. And we're going to go, half will be down and we'll go to the anechoic chamber. That's where we do our antenna testing. The other half will stay in here. We'll kind of talk about some of the projects. Then what we're going to do is when we come back, we'll have the other half of you sort of pile over onto this side of the room, and we'll bring the other half in like this, and we'll just sort of squish you guys out, and we'll rotate out, just as a heads up. We do this tour a lot, and this is one thing that makes it fun for us. So I haven't tried like an interweaving or something like this. It's kind of advanced early morning group stuff, but this works. We know it works. So I guess we'll go ahead and it looks like kind of a natural division right here, maybe. I think that's pretty close. Maybe we'll get you guys in here. Father, son? House divided. Okay, you guys can go together. You guys come up with this. Okay, you guys start coming out in this direction. And you guys just kind of hang out here, and they'll start talking about some demos and some other stuff. And then David, Shuli, and David are going to take you guys down to the anechoic chamber. So you guys can push over in this direction, and they'll get you going.
So my name is David. I'm a PhD student here with Dr. Huff. I've actually done my undergrad, master's at A&M as well, so I've been here a long time. So if you have any questions just about A&M in general or the electrical engineering department, feel free to ask me because I've been around a while. So what we're in here is the anechoic chamber. This is where we do our antenna measurements and so forth. If we just pause for a second and just kind of listen, you'll notice it's kind of quiet. The idea is that it's not really designed to be necessarily acoustically quiet, so we're not necessarily dampening sound, but the idea is that we dampen electromagnetic waves in here. So what we do is, let's say we build a new antenna and we want to test it. So we'll get our new antenna and we'll bring it down there and put it on that stand down there. On this end we have what we call here is a horn antenna. This is a very precisely manufactured antenna, so we know exactly how it works. and it's designed for a specific frequency range. We have different sizes of these things, and basically it will launch electromagnetic waves down the chamber towards whatever antenna that we're testing. And in fact, we also launch waves from that, and we measure it with this, I should say. And so the idea is then we can characterize the antenna that we're testing to understand how it radiates, which directions it radiates. You kind of think of it like a flashlight. If we had a flashlight down there and we shone it down in this direction, we're kind of just capturing the electromagnetic waves that it's radiating. And so the idea behind all these cone-like objects that you see in the chamber is to really kind of dampen out all the reflections of the electromagnetic waves. So the material itself is kind of lossy in the sense that it will attenuate the power of the electromagnetic waves. And also what happens is the wave comes in and it gets kind of caught between the cones and starts reflecting back and forth, and it just slowly kind of dissipates as it moves in. So the idea is that we only want to measure what the direct path of waves coming from our test antenna. We don't want to have a bunch of reflections coming in. So that's kind of the basic idea behind the chamber. The material on the cones is kind of nasty. It's got arsenic in it. It's one reason we don't want to touch it. It's not necessarily poisonous arsenic, but it can cause problems. It's also messy. It kind of gets everywhere and gets everything black. So that's another reason we don't want to touch it. That's kind of the basic idea behind the chamber. If you'll have any questions about kind of what this is about, or just anything more general, I'd be happy to answer them.
We have plenty of time for questions.
Yeah, we have plenty.
Any one better than the other in terms of consolidation or spread apart?
I know people. I mean, you may be in a building where there's all the labs together, and you may never once talk to the person in the lab next door to you. Here, we do. It really depends on whose lab it is. You know, when I do wireless electromagnetics, I consider electromagnetics to be a part of everything. So I have no problem butting in on some other thing that someone else is doing and going, well, I bet we could do something with you guys. That's just how we get involved. Some people like to work alone. Some people love to have cross-lab, collaboration. At any university, whether your labs are all in one building or dispersed, it's really not the location of the lab, it's the culture of the lab and the way that they interact with each other. And so it's not necessarily a matter of location, it's just a matter of, personnel. But, we do, and, I have collaborations with ocean engineering and aerospace, mechanical, civil. We've got some civil. We've got, you name it, we kind of play in it. And Frank, who you're going to talk to in a little bit, was an aero student who wanted to do some antenna stuff. He was an undergraduate. He worked with me for a long time, and he became a graduate student, PhD student. And Amanda, who's in the other room, actually was also an aero student. The aero department was angry with taking their good students, but they wanted to join electrical because they liked what we did. And we've had some people say, I want to do aero or something, but usually we do all the stuff that a lot of the other departments want to have people doing. If you want to build a robot, you have to understand electronics. And so we do electronics. And so somebody might come and say, hey, we want to do a joint project. Cool, that's great, let's do it. I got a material science project. I do a lot of material science. I want new particles. I want to make new little nanoparticles, something like this. Okay, I got to have somebody grow these. Well, I have to understand a little bit about how these work too. So that means now we've got material science students working with our antenna engineers, with our circuit designers, with our system development people. And so it just, I do really multidisciplinary research, and so do all these guys who work in the group. And it really depends on the culture of the lab and the people who do it. Some people really like the stovepipe, really get up there and do something very specific. We like to we do specific things, but we branch it out and we do other stuff. And like David, his master's was working on this little ball antenna structure, and that now it's sort of, pardon? Yeah, you'll see that in the other lab, but it's transitioned into its own project now, and he kind of gets to sit back and watch what happens to it, and every once in a while just help out a little bit and see what happens when we put this thing in the water as a buoy network, and it's taking data and doing detection of when people walk between all these little nodes and sort of figure the stuff out. So it really depends on the lab. It's a good question.
Let's make reference vertical. So it starts out, line, they're both vertically polarized, so very strong signal up front, and as it turns around, you can kind of see how it fades off. Any questions about what's going on here? I know most people don't have a lot of understanding of what antennas really do at the very start. Yeah.
A little bit off topic, but I was wondering if you could still transmit a radio signal without an IC chip.
Well, you need some sort of, you need a transmitting device, and that transmitting device is typically an IC. So, I mean,
yeah, you can transmit pure voltage and current signals, but in order to encode information into it, you do need some sort of IC that sort of modulates it.
yep. So that was the vertically polarized.
So in this case, what we have is a very viscous oil coming in and shearing droplets of a certain type of media, cells, toxins, or something like that. And so because of the shear force of these droplets, basically we're able to shear off these single tiny picoliter droplets and encapsulate cells with culture media or toxins. And we can combine these cells or toxins together, and we can screen for certain types of resistant strains or mutants that we're looking for. So in normal conventional assays, what they're doing is they're inducing some type of mutants, they're plating these on culture plates, and they're trying to basically pick certain colonies or pick certain cells and find the mutants in that type of assay. In this one, what we're doing is we're encapsulating these single cells, and we're screening them using an on-the-fly, very high throughput system. So for them, it normally takes weeks. For us, it'll take one single day, 24 hours to run the entire system. And so if you can imagine, you have like 1 out of 1,000, 1 out of 10,000 of these droplets that has some special characteristics, some mutants, some certain type of resistance. And so because of that, what we'll do is we'll tag this cell so that whenever that resistance is present, it'll fluoresce. So we'll get some type of fluorescence of the cells. And then we'll be able to isolate that, so we'll detect these cells on the fly using some type of optical fiber detection system. And then we'll be able to sort these single droplets out and harness that droplet and reculture them, put them into like a DNA sequencer, find out what's making this special or what type of genes are being produced that makes this special. And then we can, from that, we can create some type of antibody or virus. So this is, this kind of goes into like also an evolutionary type study. This project is funded by the DTR, so Defensive Threat Reduction Agency. And so what normally happens in the environment is you have a certain type of cell, and they'll slowly get a certain stimulus. So, and over time, they'll grow resistance to that stimulus. So what we're doing is we're basically creating small interactions and forcing this stimulus over and over repetitively, and then over a course of time, one of these cells will have that resistant type of gene. We want to harness it, find out what's making it resistant, produce some type of antibiotic, so that way in the environment, if this certain type of toxin is being produced, we're able to suppress it, or create a vaccine, or antibiotic, or antidote ahead of time. So this is kind of getting ahead of the game. So this is just the overall schematic. There's a lot of other different fluidics types structures. So in this one, we're basically just using a trapping structure. So we just have a valve on top where we can just press these traps. So we capture a single cell inside of this trap, and we're able to flush media to keep it very healthy over an extended period of time. So we're talking about weeks, and then we're able to induce some type of toxin, and then see whether a certain microbe or cell is producing some type of resistance or special characteristics, and then we can release that one trap. And so this one is actually an array of traps, so you have a bunch of different traps, but by using a multiplexer network, we're able to release one single trap and then harness that one cell that we're looking for. So this is just another one. So here we're just basically showing we can release one single trap out of the entire array. So every single one of these is filled with one cell, but we're releasing one at a time. So that's what makes this special. So this certain application that we're doing is for renewable energy. So algae, they normally, certain types of algae that we're working, specifically the ones that we're working with, they produce oils. And these oils can be broken down into basically fuel, diesels, jet engine, regular car gasoline. And so because of that, there's a lot of interest in looking into these certain types of algae to harness them for renewable energy. So in this video, we're basically just showing that this algae that we're looking at can produce this type of oil. So by squeezing this algae, we can harness this oil and then break it down into renewable energy. And so what we're doing is we're taking these algae and we're inducing some type of mutation into them so that they either grow rapidly or produce a lot more oil than the normal algae, and then we select that one algae that is special, that's producing a mass amount of oil or growing rapidly, and then we'll basically create a large bioreactor and be able to produce a lot of this oil for renewable energy purposes. So right now, the thing that is limiting this is that these algae grow kind of slow, don't produce a lot of oil, so we can induce a certain mutant, get that 1 out of 10,000 algae that produces a lot of oil, then we can make this a feasible, economically feasible to be able to produce this type of oil. So in one of the platforms that we're using, basically what we're doing is we're controlling the light conditions on this platform. So we have basically a dark and a white, two fluids that are flowing through, and this can control the light, how much light intensity each algae is getting over a certain amount of time. And we can, and using this bottom layer, we can also control the different light cycles. So if you have the light on for 3 hours, 4 hours, 6 hours, so depending on this light cycle, it also affects how the algae grows over a certain amount of time. And so using this fluidic type system, which is the same as this except it's 3 layers stacked on top of each other, we're able to control the entire light system of this algae population, and then find which one is growing rapidly due to a certain light condition. Use that light condition in the conventional large bioreactor facilities. So because of this, we also need to screen for which ones are producing a lot of oil or growing rapidly. And so one of the interests, as I mentioned before, is we're creating these small droplets. One of the things that we're doing is we're staining these cells with what we call Nile red. It's basically just a fluorescent staining material that stains the oil inside of the cells. And so what you have is you have some droplets with Nile red and some with cells that are combined together. They flow into this channel, but because the Nile red stains anything that's hydrophobic, this oil, so as I mentioned, this is a droplet with media, with cells. Outside this is oil. It's just regular mineral oil, not the oil that we're harvesting. But inside of here, there's small algae that have the oil that we want. So because there's this oil on the outside, the Nile red also stains this oil. So what this is this is a pillar array structure that's rinsing all of the fluorescent background so that we can harness these droplets that just have the Nile red with the algae stained with the Nile red inside them, so that we can do a section. So all we do is we flow these through a detection system. We have some light source that causes the cells to fluoresce, and then we're able to see which one fluoresces a large amount and then harness that single one that we're looking for. So you can see all the oil that's stained, which is kind of bad because it wouldn't be able to do detection, goes out to the right, and then we're able to get a clear black and white signal from the cells. So this is just an example of the overall system. So basically you just have the generation of the droplets here on the left side. You have the synchronization of these two droplets. So here we just use a railroad-like structure because the equal of the flow resistance between the two trains might be different. So what happens is if you have the two droplets that are staggered, the flow will actually go around in the path of least resistance, which is the same in electronics. And it will allow these droplets to catch up to each other, to synchronize one-to-one, so that we can do the merging between one of each of these two droplets. And what we normally do is we apply an electric field. So you see here there's 2 electrodes, and we just make one 0, one as a positive, and we apply a pulse AC signal. And what this does is it induces an electric field in between these 2 electrodes, and it allows these droplets to merge. This is basically done by destabilizing the droplets, aligning the droplets together, so aligning their dipole moments, and then allowing them to merge. So this is how we combine 2 samples together on the platform. Basically then we just mix them together, culture them for a certain amount of time, and then let's say you have one of these that is special, then you want to be able to sort that one or grab that one and throw away the other 10,000. And so what we have is optical fiber system with an LED. So conventionally this is done with a microscope. So normally you just look at the sample, see which one fluoresces, and then you try to grab that sample, right? But what we're doing is we're replacing this microscope system and put it all on a chip, a small chip like this. And so what we have is just an LED. The light runs through the optical fiber, excites your sample, runs through the other side of the optical fiber, and then you just have a detector, which is kind of like an eyepiece. So you can detect the signal, see how much of the signal is there, and then from there you can sort it using either pneumatic valve sorting, acoustic sorting, so using waves, or also using an electric field, which I'll talk about and show a little bit. So normally these droplets are generated, as I mentioned, using oil. So here you just have the oil inlet and water inlet. So this is just a short video. So you can see this is very fast, high throughput. I think this one is probably like 20 hertz or something. So thousands of droplets being produced and this is real time. Thousands of droplets being produced at a time.
On my iPad, isn't it?
The image?
Yeah.
So this one I think is at like 5x. Each of these droplets is around 100 micrometers.
Okay.
So I mean, the cells that we normally use are anywhere from around 5 micrometers, for instance, like E. coli, up to the algae are around 50 to 70 micrometers. So this can encapsulate one single algae, or 100 to a couple hundred E. coli.
This was co-founded by Professor Srinivas Shakotai. Unfortunately, he's out on the conference, so he couldn't make it. So I'm here on his behalf to give you a tour of the lab. And let's see. These are just some of the students here. One of the students is Suman Paul, near the back. He's a graduate student. This Shapira, he's also a master's student. And this Jian is back, he's a PhD.
Hi.
My name is Rajarshi, I'm also a PhD student here. Let's start by saying that the current world today is always kind of interconnected world. And then there are networks everywhere, whether you say it's a social network, like something you have with your family, connections you have with your family, or a natural computer network which moves packets across the internet. And then there's this increasing use of smartphones. Some reports say that almost more than half of the US population now have smartphones. And now the smartphones are equipped with a large number of sensors, like the gyroscope or the GPS, or even some have barometers and stuff. So it's actually a good way of accumulating information from your surroundings and get to analyze the data and get to know something meaningful out of it. As part of the group, we have a number of courses that give some basics of computer networks. Like Isian said, 4 to 4 was taught last semester. It had about like 30-35 students, and they professor talked about the basics of computer networks, the protocols and stuff, and basic communication like socket programming. I won't go into the details because that won't be very interesting. Innovation Laboratory was another one of these courses that were floated some time back. And here we use more of microcontrollers and sensors along with smartphones to get some useful results. Like one of the good projects that were done was there were a group of undergrad students that put up a number of sensors on the parking lot there, and then there was this app that was integrated, so we can get real-time information about the slots that are available, whether they're filled, and it was pretty useful. People used it and they were happy. Android Club is more like an ad hoc initiative, you can say. People who are interested in computer networks as well as Android, they come by and like brainstorm together, get some new ideas, they build applications and stuff. So it's a pretty cool process. I think I have a demo. I have a demo by one of the graduate students here.
Hi, I'm Mike Manjikar. I'm a graduate student with the Department of Electrical Engineering at A&M University. Today I'm going to show you an Android application demonstrating basic principles of digital communication. Using the Android software development platform, we have developed here an application that uses frequency shift keying to communicate a message over the audio spectrum. We start off with embedding.
Let me explain this. This is actually not a very complicated system. We have a message like welcome to Aggieland, as you can see here. What we try to do is we first convert the message into binary 0 and 1, because that's how we convert. And then we encode it using this modulation scheme into audio signals. Now, these audio signals can be transmitted using the speaker, like our phone or our laptop or whatever device you're good with. And then on the other hand, the microphone that is on the phone, the Android device, gets the signal and then decodes it and then is able to get back the message.
Message into bits using ASCII encoding. the frequency shifting mechanism roughly means to transmit a bit 0 using a tone of one frequency and transmit bit 1 using another frequency. Thus, the stream of zeros and ones is converted into a voice message that can be played out by the speakers. At the receiving end, the Android device captures this voice message using its built-in microphone, processes it, and decodes it back into the original message. Once the recording is complete, the device needs to locate the start of the message to begin processing. To enable this, we add a preamble and a pre-agreed synchronization pattern before the transmission of the intended voice message. The application's interface uses a simple layout with 2 buttons. To start recording, we press the record button, and once the signal has been recorded, we press the stop and decode button as shown on the right. The Android device then begins to process the voice signal, during which the interface is kept busy, and once the processing is done, the decoded message is displayed on the screen. Let me now demonstrate to you the working of this application. For the purpose of demonstration, we use a laptop to transmit the voice message, but this could have easily been done using another Android device.
This beeping sound that you can hear just now is actually the encoded signal in audio that is being transmitted from a laptop to the phone. Now he is decoding it.
Has now started to process the voice signal. It is interesting to observe the speed-based Android device has performed the computationally expensive task of decoding, which further emphasizes the powerful capabilities of this platform. Thank you for watching my presentation.
So like he says, Android is useful because modern smartphones nowadays come with good processor capabilities. So actually, if you have a computationally intensive task, even like the encoding and decoding that you can see here, it's able to do that pretty fast, and the outputs are really good. I'd like to talk a bit about the research that we are doing now. It's based on a simple idea that modern smartphones nowadays have multiple interfaces, like the expensive 3G interface that you have to pay for, and the non-expensive Wi-Fi interface. So the idea is that suppose we have a group of people together in a room and they want to suppose see a live video stream. Now if everybody of you were to download the entire video stream, it would be very expensive for all of you. So instead what we do is we divide the download among ourselves, like suppose you download 10% of the data, then you download the next 10%, and then you share among yourselves to get the entire stream. So it's like this, like suppose it is the entire file data stream that you require, you divide it up into chunks and then get different chunks through the 3G interface. Now this will decrease the amount of money that you need to pay for the 3G service, and then you can share amongst yourselves in the local network and get back the entire stream. Suman has a demo that is currently working for that, for this project.
So I'll show you an application that I'm working on to demonstrate what we just said. So this is your everyday smartphone, there's nothing different about it, only that this runs a modified version of Android. So what happens in your smartphones is that when you come home or you go to a friend's place where you have a Wi-Fi network that you have already used and set up, so what it does is it switches off your 3G and switches to your Wi-Fi in order to save your 3G data costs. So what this phone does is it doesn't do that. What it does is it always has 3G and Wi-Fi connected. We have modified the Android in such a way that the two interfaces always work together. And this, I use this phone for everyday purpose, so you can actually use such a phone. It doesn't cost you anything extra. So what happens is that here I have my server in my desktop. So what it does is all these three phones connect to the server, and instead of downloading, I'll show you a audio stream. We are working on video as of now. So what it does, it connects to the server, and instead of sending 100% of the data to all the phones, what it does, it sends only around 50% of the data. So what you're doing is when you are listening to the stream, you're actually saving 50% of the cost by sharing the remaining 50% amongst yourselves and downloading only 50% from the server. So I'll just show you a demo. when you connect to the server, it shows you a simple UI and it says what frame number you are on. So it shows it's just it's still experimental, so it often crashes. It accumulates the data and then it plays for a couple of frames together. So let's see. Yeah. So this is the data is sending this desktop is sending. So it sends only 50% of the data to each of the phones. So essentially you're saving like 50% of the data if your data costs. So maybe in the future sometime you might see this kind of thing, but it doesn't make much economic sense to your carriers because they only want to make money for you. So it might be some time until you see such things in your real life. So, but yeah, that's the summary.
So Professor Shakata actually had a grant from Google, so he got like about 20 HTC Evo phones, and that's how we started developing on Android. As part of one of the courses that I showed you, the undergrad guys had actually made some cool applications using Android. They had worked over 3 weeks on this lab, and so we get pretty good results from this. And if you have any questions for me?
Yes, so one of the main things is that we will not teach. The aim is not to teach Android programming or anything. It's just as a tool to do your stuff. But the main aim is to teach you the essentials of your networking, wireless networks, or computer networks. We just use Android as a tool for development to show our ideas that it's actually doable.
Yeah, and it's open source, so there's a lot of support out there.
Yes, so if you have any questions about the application or anything, say.
So would that work like a peer-to-peer network between phones? Is that what that is a little bit?
Yeah, this part is the part that's sharing.
Yeah.
Is like
peer-to-peer network.
So it's not actually pure peer-to-peer. So it's a part peer-to-peer and part you're downloading it on your.
Yeah. Yes.
So yeah. Okay. So part of the data is being downloaded and the other part you're sharing it amongst yourselves. Okay. So it's very much like your BitTorrent networks if you're familiar with that. Like it has to be on our present-day phones. They don't allow you to run two interfaces at the same time. So every time you see your Wi-Fi network that you know, it automatically switches off your 3G and then switches on your Wi-Fi for data. So this we had to actually modify your Android code so that both of them work together at the same time. It has some glitches, but then it does work most of the time. So often it would like switch off connections and you have to reconnect, but then it does work pretty fine.
So how long does it take to build an app like this?
It takes some time. So what I told you is like a very high level overview. We have been working on this for like 1.5 years now. So because we have to do a lot of other stuff, like modify Android, and there's a lot of algorithms and other stuff going on in the background. So it does take some. But simple apps like the one he showed a video of, you can build it within a semester. It's pretty easy to learn.
So basically, students work on these kind of apps. Or
yes, in your 424 projects, students do build Android applications. So in the end of the semester, they have a project kind of thing. So they work in groups and do build some. It depends on your level of interest. So you can go for complicated projects or simple things. So kind of stuff.
So at the Aggieland, did you focus more on IPv6 now?
No, we still using IPv4.
Or IPv4? Is IPv6 pod?
I think that our infrastructure is not yet ready for IPv6.
Not everything is ready, yes.
Yeah. So I think companies are working on moving towards IPv6, but it's not, because I talked to Cisco and they said that they are like trying to move, but their infrastructure is not ready. So it needs some time yet. Yeah, but I think Professor Shakura does teach about all this stuff. So it's there. I mean, that's what it's taught in the courses.
So if you don't have any more questions, then thank you for visiting the lab. Have a nice weekend.
Howdy, we're IEEE. We're the Institute of Electronics and Electrical Engineers, and one of the major things we're doing this semester semesters are microcontroller projects. My own projects are down here. I've got a music reactive LED strip here, and I've got a scrolling text here with Gigam for the day, and that's driven off of an MSP430 microcontroller. We've got another couple of projects going on. We do socials, we do corporate outreach, we have companies come give us talks, and we're going to be hosting the MicroCon this semester so that you can come out and build your own projects, show them off, and get some prizes. You can check us out at IEEE.org.
Hi, this is Ada Kappa Nu. It's the Honor Society of IEEE. It's just a sister organization. We do things such as service and social events. We also get companies to come through, such as Boeing and IBM. It's a great opportunity to build your resume and get involved. There's another reason to get your GPA.